Whenever you're doing Laplace transforms on piecewise functions, there's actually a way better way to do it than the way we're going to start off doing it, but I think doing it the long way will help us whenever we do the derivation for like the general way, just because you'll see like some similarities and stuff. So let's pretend that I don't even have a clue that there's an easier way to do this, and I want to find the Laplace transform of this function. Good? Exciting? Yay. Okay, so I'm starting off with this. Now the first thing that I want to do is I will set up the two different integrals. So basically, if I'm going to be integrating from 0 to infinity, it's e to the negative st times the function 2t plus 1 dt. Except that the function is not equal to 2t plus 1 all the way to infinity, it's only equal to 2t plus 1 up to 2. So I'm kind of stuck. All right, the rest of it is, again, possibly I would say 0 to infinity, e to the minus st, except writing is hard, e to the minus st times 3t dt. But again, this isn't actually defined from 0 to infinity, it's only defined from 2 to infinity. And you're like, oh, this is amazing. Okay, so here's what I'm going to do. I'm going to come through here, and because this makes perfect sense, and why wouldn't you do it, I'll say 0 to infinity, e to the minus st, 2t plus 1 dt. And then I'm going to, so basically I'm going to integrate from 0 to infinity, but I'm going to subtract off the 2 to infinity part. You're like, that seems like a total waste of time. And I'm like, I know, but it's like important and stuff. And then I'm just going to leave this the way it is. All right. So the reason that I would do this is that this guy, well, this right here is the definition of a Laplace transform. So Laplace of 2t plus 1. Yay! And then basically what I'm going to do is I have plus this stuff minus this stuff, except that it's like on the same, whatever you call those things. I just erased my D. It's on the same, those thingies, limits. It's on the same limits of the integration. So basically what I can do is I can combine them. And I'm going to list the second one, or the third one first, and the second one second. Anyway, I'm going to go 2 to infinity, e to the minus st, and I've got 3t minus 2t plus 1. Good? Good. Yay! Okay, so Laplace of this thingy plus 2 to infinity, e to the minus st, and then that turns out to be t minus 1 dt. Now, I so much wish that this was a stupid 0, but it's not. Okay, so we're going to do something kind of similar to how we were doing, like changing the limits on summations. Or you might not even think about summations and just think about it as being like, whatever you call that, substitution-y stuff with integration. So what I'm going to do is I'm going to let some other letter, I don't really care what it is, I'll make it v, so how many v's? I'm going to let v equal t minus 2. You're like, why? I'm like, I don't know, because I said so. Because I wish this was 2 less. Okay, so basically what I'm going to do is I have dv, or t, but v equals t minus 2, so that means that dv is equal to dt. Okay, so this guy at the beginning is still fine because he's in terms of t, and I'm going to leave him that way. 2t plus 1. So basically what I'm going to do is I have the limits on my integration. Okay, so this is going to be, in the new terms, in terms of v, the new v is going to be the previous t minus 2. So if you've done limit changes or substitution with integration, this isn't a big deal at all. But basically I'm going to go 2 minus 2, so that's 0. Infinity minus 2 is still infinity. Okay. T, let's see, I could also say that t is equal to v plus 2. So basically I'm subtracting 2 off the limits and I'm adding 2 inside. So this should kind of, except you can't see what I'm doing, this should kind of remind you of doing blah-like stuff. And we do like, we'd be like, okay, I'm going to add 2 to all of these, and then I'm going to subtract 2 here. That's kind of what we're doing, because remember that integration is just like super infinite summation. So it's really the exact same thing. It just, we do it officially with calling it a u substitution and going on from there. So anyway, t is equal to v plus 2. So I have es t plus 2, and then I have t plus, oh, not t plus 2, v plus 2. V plus 2, and then I have v plus 2 minus 1, and then dt is just dv. Okay, then I do this. Oops, plus. All right. So I have this guy right here is e to the minus SV times e to the minus 2s. Now, e to the minus 2s can come directly out because it's not in terms of v, so with respect to v, it's just a constant. So I can pull that out, and it's kind of nice. So I have e to the minus 2s, integral 0 to infinity, e to the minus sv, and then v plus 1 dv. All right? Now, I'm going to do something that's going to really upset like most of the people on the planet that care enough to watch this video, is I'm going to let t equal v. And you're like, but we just had a t. Is that the same t, or is it a different t, or is it a whatever t? And it doesn't matter, because it's just t. So essentially, think about this. So we had, going back to this example, in previous videos we've had these infinite sums, and we had like n, and then we had x to the n. And we said, well, I really want this to be, I know I just did this, but just bear with me. And we said, I want this to be minus 2, so I'm going to add 2 to both of these. And then we ended up with this lovely little equation that was n equals 0 to infinity, a n plus 2, x n plus 2. But riddle me this? No. Think of it this way. This is another way we could have done it, is we had this. Now, what I could have done is I could have said, let, I don't know, r equal, what would I let r equal? Like n minus 2? And then I could have said, so that means that n is equal to r plus 2. Then I could have come through here, and I'm going to do a change of base. So everywhere I see an n, I'm going to put an r plus 2. And then remember, this is really n going from 2 to infinity, so instead of n, I'm going to go r plus 2. And then everywhere I see an n, I'm going to keep putting an r plus 2. And everywhere I see an n, I'm going to keep putting an r plus 2. So then, if I subtracted 2 from both sides, I would get r equals 0, subtract 2 from both sides, and again, infinity minus infinity is just infinity. And I have a r plus 2, x to the r plus 2, and you're like, but over here I had n's and here I have r's, but it's just what you're summing on, right? So what you're summing on is just like what you're taking the integral on. So really what I could do is I could now just come in and say let r equal n, because it doesn't matter. Everywhere I see an r, I can replace it with an n. So like basically what you could do at this point is you could say, okay, now I'm going to pretend that this up here never existed. And what would I do if I just had this by itself? Oops, not like that. What would I do? So if this had never existed, and I just had this over here by itself, what could I do? And I could say, well, I don't like it in terms of r, so I'm going to let it be in terms of n. Is it the same n I had before? No, but it doesn't matter, because at any step in algebra, I should be able to step into it and get the exact same thing, not dependent on what happened in the past, because every time I write it, it should be a completely valid equation. Okay? So with that in mind, and I know that this is kind of a little esoteric or weird or something, whenever you come up to here, and so we had this let t equal v and all that, but really what I could do is I could just pretend what I would do if I was just given this equation by itself. And somebody just said, simplify this, okay? Somebody just gave me this equation and said, simplify it. I'd be like, well, that looks like it's supposed to be a, whatever you call it, Laplace thingy, except that we don't usually look at Laplaces as being in terms of v, so I'm just going to I'm just going to substitute in t for d. Everywhere I see a v, I'm going to write a t. And so whenever I do that, now you might say, well, there's this part out front. Well, that's okay. I could let this equal x, and then I could put the t in, and it'll be fine. Trust me. It's all going to be okay. And so now I'm going to integrate. So just like I changed the base on the summation, I can change the base on an integration, because integration is just like, summation on craziness, and that's okay. Okay, so the whole point is, now I have the Laplace transform of 2t plus 1 plus e to the minus 2s times the Laplace of t plus 1. Okay, you're like, that's absolutely insane, but at least now I can do it, so I have 2 times 1 over s, 2 times 1 over s squared, right? T squared, the t becomes s squared, and it's over, yes. 2 over s squared, 1 over s e to the minus 2s, and then again 1 over s squared and 1 over s. Now there is an easier way to do this, but I just kind of wanted to walk you through this little part of it so that you can see, and you can't really tell what's going on anymore because I've zoomed so far out. But basically what you'll see is as we go through here, what we had is we had basically this part where we had to have this 2, and this 2 became this 2, and that 2 followed around to here, and so that's where this 2s is coming from. That 2s is coming from the fact that our piecewise function stopped off at 2, okay? And then you can also see that the first part of our Laplace, or of our piecewise, the 2t plus 1, is just right here, and it's perfect for all the world to see. Now, it's a little bit more obscure to see how that turned into t plus 1, but we're going to go do that separately. I just kind of wanted to walk you through a numerical example because I think that the formal derivation is just a little funky, so we're going to go do that next. So assuming you're still with me, we're going to see what we can do with a regular Laplace thing. Okay, now at some point in another video we talked about how I can rewrite a piecewise function if I had 2t plus 1, 3t, 0t, 2, and it doesn't really matter where these are going to be for the moment. So I said that I could rewrite this as I've got 2t plus 1, and it needs to be multiplied by a unit step. So ut minus 2. So it needs to be multiplied by a little top hat. And then 3t needs to be multiplied by ut minus 2. Okay, so if I was going to Laplace something, I would be Laplacing this. And then I'd be Laplacing this. And then I'd be Laplacing, well, if I combine those last two, I would get minus, I'll do it this way, 3t minus 2t plus 1 times u of t minus 2. And you might kind of have an aha moment here in a second. So I've got ut, and then 3t minus, well, that's just going to be t minus 1. And that's where that t minus 1 comes in, ut minus 2. So what we're going to focus on specifically is how do I find the Laplace transform of something that looks like this? Okay, so that's what we're going to focus on, and then we can come back and we can take the Laplace of it this way. So the idea would be that instead of having all those like separate integrals that go from here to here, and from here to here, and here to here, I could just write it as a piecewise function and then take the Laplace of this thing, like this, and that would be easier, but I have to figure out how do I take the Laplace of a unit step. So now we're going to pretty much do the exact same thing we did before, except we're just going to use functions instead of like normal things, and that's okay. So say I have some kind of unit step that's shifted, g of t. Good? Okay. So if I go back to my basic outline, then that's going to be 0 to infinity, u of t minus tau, g of t, e to the minus st, dt. Got it? Okay, now, since I'm multiplying by this unit step, that means from 0 to tau, the value of the function is actually 0. So I can just say 0 dt, or not even listed at all. And the rest of the integration goes from tau to infinity. So I'm just going to write the whole thing again, from tau to infinity. Just like that. All right, then we're going to do that thingy again, where I'm going to let v equal t minus tau. So dv equals dt, and t is equal to v plus tau. T is equal to v plus tau. Beautiful. Okay, so I'm going to subtract tau off of here and here, minus tau. That still goes from 0 to infinity. T minus tau is v, so u at v. That looks a little funny, but that's okay, because we're not afraid. We're not afraid. T is equal to v plus tau, and it's e to the minus s v plus tau, and it's d something, dv. Okay, now again, keep an eye on your other notes and relate what we're doing now to what we were doing then. So uv, actually, so here's something that's kind of neat. So now that I've done this, u at v, right, is basically just 1 from 0 to infinity. So this is, the value of this is just 1. So I don't even have to list it anymore. So I've got g, v plus tau, e to the minus sv, e to the minus s tau, dv. And this is just a constant with respect to v, so I can pull it out front. So e to the minus s tau, and then 0 to infinity, g, v plus tau. My kitty cat just jumped halfway up the wall. That was very entertaining. dv. And because I can pretend that I've just been given this equation out of the blue, I can just decide arbitrarily I'm going to let v equal t. And then I can rewrite the whole thing. E to the minus st, integral 0 to infinity, g, t plus tau, e to the minus st dt. And now I can very delightfully discover that this is just the Laplace transform of g of t plus tau. So essentially what we've done is, if you go all the way back to the beginning, what we were doing, we said that if I take the Laplace of u of t, there we go. Sorry about that. U of t minus tau, g t, is equal to e to the minus s tau times the Laplace of g of t plus tau. Okay, so maybe that makes a little bit of sense. Maybe it only makes a 0% part of sense. But what we can do is we can now use this to do the other piecewise integration-y thingy, whatever, a whole lot easier. Okay, so remember, so this is like a new thing. This is really important. Super important. Okay. So what we had before is we were trying to take the Laplace transform of 2t plus 1 that was multiplied by a unit step just by itself, and then t minus 1, and I'll rewrite it in the same order because we've got the units first. So I have u of t times 2t plus 1, and then u of t minus 2 times t minus 1. All right, and we wanted to take the Laplace of that. Okay, so let's do the Laplace of the first one. So let's do the Laplace of the unit step of 2t plus 1, and then the Laplace of the unit step of t minus 2 times t minus 1 to do. Okay, the first one is actually a lot easier than it looks, because in our case tau is equal to 0, right? So if I'm looking at this, this is my, so I'll write this down here. So in this case, tau is equal to 0. So if I'm matching piece by piece, okay, and then and so this is that g of t is equal to 2t plus 1. So over here on the right, that's going to become g of t minus t plus tau. So if I want to find g of t plus 0, well, that's kind of stupid looking, but everywhere I see a t, I put a t plus 0. So I get 2t plus 1. So I get the same thing back, which was kind of a waste of time. If this is creeping you out a little bit, it's just the same idea as if I had like g of t was equal to 2t plus 1, and then I want to find g at 3. You know, just everywhere I see a t, I put a 3. So that's really all we're doing there, is just that. And it looks a little weird because we're doing it at tau equals 0, which means it's kind of useless. But that means that I get e to the minus s times 0, which just goes out to be 1, times the Laplace transform of 2t plus 1. And you're like, I feel like I've accomplished nothing. But that's okay, because you learned something. Because it'll be much more interesting when we apply it to this guy, because here tau is equal to 2. Okay? And in this case, our g at t is equal to t minus 1. Okay? So this is our g of t, and it's t minus 1. And now I want to know what is g of t plus tau. So everywhere I see a t, I put a t plus tau minus 1. So that's equal to t plus 1. So now I'm going to add the Laplace transform of e to the minus s tau times the Laplace transform of g of t plus tau, which is t plus 1. Now this should look super familiar, because this is basically exactly what we already had before, except that we don't have to do all the math to make it happen. So the Laplace transform of 2t is 2 over s squared, and then 1 over s, and then e to the minus 2s times the Laplace transform of t, which is 1 over s squared, and 1, which is 1 over s. So this is probably the trickiest part for me, is getting this straight. Actually, the trickiest part for me is doing this backwards. But hopefully this is at least an introduction to what this looks like. I'm going to do another video that just has a just ridiculous ton of examples for you to play around with. But this should definitely be enough to get you started.